Welcome to This Explainer. Today, we're staging the ultimate clean energy showdown. We're tackling a question that is absolutely pivotal to the future of our entire energy infrastructure. Can hydrogen truly dethrone the lithium battery? The answer to this is going to completely reshape how we engineer our world over the next few decades. Let's get into it. Just imagine for a second a sudden, radical shift in our energy landscape. What if the lithium batteries powering the millions of electric cars on the road today just disappeared tomorrow? Could hydrogen step right up and become the next ubiquitous energy revolution? You hear it all the time, right? Hydrogen is frequently hailed by engineers and energy analysts as the true fuel of the future. But can it practically replace lithium batteries at scale? Well, the answer is a lot more complicated and honestly way more fascinating than a simple yes or no. Section 1. The Reign of Lithium. To really understand why lithium dominates right now, we need to bypass our basic day-to-day experience with it and look right at the fundamental mechanics. A lithium battery operates as a closed-loop direct chemical storage system. You pump electrical energy in, and it forces a highly efficient kinetic-to-chemical conversion without any intermediary waste. It's incredibly reliable. It just holds that state until a circuit is completed, releasing that electricity exactly when you need it. So think of it as a super direct, straightforward process of capturing and deploying power. And that directness, that's exactly why lithium is so successful. It all comes down to a few undeniable strengths. First up, high efficiency. We're talking round-trip efficiencies north of 90%. Basically, you get out almost exactly what you put in. Then there's the fast response. Power delivery is literally instantaneous, available the exact millisecond an electric car motor demands torque or your phone's processor requires voltage. Add in its compact size, which lets us pack dense energy into tight spaces, and the fact that it's a super mature technology. We already know exactly how to manufacture, scale, and optimize these cells all over the world. But, as amazing as it is, our current heavyweight champion does have some pretty severe vulnerabilities. Mining lithium and processing the required cobalt and nickel, that demands intense geological resources and massive amounts of localized energy. It creates some really complex supply chain bottlenecks. Plus, just basic battery chemistry dictates that performance is inevitably going to degrade over time with repeated charge cycles. We've all seen our phone batteries die faster after a year or two, right? And critically, for big macroeconomic grid applications, long-term storage is just incredibly cost-prohibitive. Trying to store the summer sun for freezing winter using lithium would require banks of batteries so massive it would literally bankrupt the local grid. Which brings us to Section 2. Enter the hydrogen alternative. Okay, let's walk through this mental model step by step because hydrogen operates on a totally different paradigm than lithium. Step 1, electrical power drives an electrolyzer to literally split water molecules into pure hydrogen and oxygen. Step 2, that separated hydrogen gas is then mechanically compressed and stored in heavily pressurized tanks. And step 3, when you actually need the power, a fuel cell passes that hydrogen across a catalyst to convert it back into electricity. So the essential takeaway here is that hydrogen acts more like an energy carrier rather than a primary storage battery. And when you tally up hydrogen's strengths based on that process, it sounds like an absolute game changer. Long-duration storage means you can keep pressurized hydrogen in a tank for months without that slow voltage bleed you get in chemical batteries. It also allows for super fast refueling. Industrial vehicles can pump a full tank in minutes, totally bypassing the downtime of electric charging. Plus, it boasts an incredibly high energy density per unit mass. But most importantly, it elegantly solves lithium's seasonal storage problem. You can run those electrolyzers at maximum capacity using excess solar energy during July, and then just burn that stored fuel in the dead of January. I know, that all sounds incredibly impressive, right? Like a total engineering slam dunk. But, well, there is a catch. A hidden vulnerability that fundamentally threatens hydrogen's claim to the throne. Section 3. The efficiency battle. Let's break down the stark numbers here. Let's say you start with 100 units of raw, renewable electricity freshly generated by a wind turbine. If you route that into highly efficient lithium batteries, you're going to be able to store and actually use around 85 to 95 of those units. Now apply that same starting electricity to hydrogen production. You lose energy during the initial electrolysis. You lose massive amounts of energy mechanically compressing the gas. You lose thermal energy during storage. And then you lose energy once again during the fuel cell conversion at the end. By the time that power actually reaches a motor, your final usable energy has plummeted to roughly 30 to 45 units. You are literally throwing away more than half your energy just moving it around. The physics here present an undeniable hurdle. When your primary objective is simply retaining raw generated energy, the direct chemical storage of lithium is just fundamentally superior. If overall thermodynamic and economic efficiency is the baseline metric, meaning getting the absolute most utility out of every single megawatt your infrastructure generates, batteries are mathematically the absolute clear winner. But here's the twist. Section 4, where each technology wins. The reality of global energy architecture is rarely a zero-sum game. As it turns out, these technologies are suited for entirely different arenas. Lithium is the undeniable king of daily, localized use. Your commuter cars, personal electronics, overnight short-cycle grid balancing, those are perfectly served by direct battery storage. Hydrogen, on the other hand, steps up to the plate when the scale gets massive. We're talking heavy, continuous haul trucking, intercontinental cargo ships, commercial aviation, and that critical seasonal energy reserve. In those environments, sheer sustained power output and longevity far outweigh those efficiency losses we just talked about. Let's break down the practical realities of why lithium dominates our daily lives. First off, the distribution network already exists. We have sophisticated power grids running into virtually every commercial and residential building on the planet, which makes localized charging almost frictionless. Second, economies of scale have driven lithium manufacturing prices down by staggering percentages over the last decade. It has unstoppable market momentum. Combine that with ongoing chemical breakthroughs that keep improving cell density, and lithium remains the undisputed, practical choice for decentralized daily power. Now, on the flip side, imagine trying to power a massive global shipping vessel with lithium. The sheer compounding weight of the battery packs required to cross the Pacific would be astronomically heavy. They would literally sink the ship. It is physically and economically impossible to scale lithium for extreme heavy-duty transport. And this is exactly where hydrogen swoops in to save the day. It can safely store huge amounts of energy for weeks or months without degradation, providing immense sustained power while entirely avoiding the prohibitive mass constraints of giant solid-state battery packs. Section 5, the future of clean energy. So, going back to our big question, can hydrogen actually replace lithium batteries? Well, not completely. And structurally speaking, it's pretty unlikely it ever will. The core takeaway from synthesizing all this data is that we have to abandon this false dichotomy entirely. The energy transition is not hydrogen versus batteries. The future is hydrogen and batteries working together. We are going to continue deploying highly efficient lithium for decentralized, daily, short-term needs where rapid turnaround is absolutely key. And simultaneously, we're going to leverage hydrogen as an industrial-scale carrier for long-duration storage and heavy transport, where physical weight and energy longevity dictate the rules of physics. Ultimately, the question isn't really whether hydrogen will kill the lithium battery. We know they serve distinct masteries within the laws of thermodynamics. The real pressing question is, how quickly can we scale both of these technologies in tandem to completely overwrite our reliance on fossil fuels? Can global manufacturing actually keep up with the massive demand for both of these parallel infrastructures? What do you think? Let me know where you stand on the future of our clean energy grid.